Well, we're going to work on questions 16 through 19. So get out your book and open it to page 74. So we've gone over how to design different experiments, how to recognize and use experimental variables, how to control or eliminate experimental variables that might affect the result of your experiment in a bad way. Now we're going to look at some experiments and get some practice interpreting their results. We're going to start with an experiment that deals with ocean water. In experiment 3.1, you mixed salt with water. You mixed the salt so thoroughly with the water, the salt seemed to disappear. It did not disappear, however. If you had tasted the water, it would have tasted salty. Thus, the salt is still there. It just mixed so thoroughly with the water that you could not see it. We say the salt dissolved in the water. Lots of things can dissolve in water, including gases. When you drink soda, for example, the fizz that comes from the carbon dioxide, which is dissolved in the soda. Carbon dioxide is a gas. It can dissolve in soda, which is a liquid. In the same way, oxygen gas can dissolve in water. That's actually how fish and other underwater creatures get their oxygen. Fish have gills which remove the dissolved oxygen from the water and allow the fish to use the oxygen to breathe. So, whether or not water can support fish depends on how dissolved oxygen is in the water. If there's not enough dissolved oxygen in the water, the fish will suffocate, just like you and I would suffocate if there wasn't enough oxygen in the air that we breathe. If you have seen a fish tank with a lot of fish in it, you probably saw something in that tank that was bubbling. The bubbling was caused by a pump that pumps air into the water. Most of the air bubbles out of the water, but some of the air, especially the oxygen, is dissolved into the water, keeping the amount of dissolved oxygen in the water high enough to support the fish in the tank. A scientist studied the amount of dissolved oxygen in the ocean water at different depths in the Bering Sea. After making his measurements, he graphed the results on the graph that you see on your book on page 74. It is important for you to become familiar with reading graphs, especially graphs like this, as a lot of experimental data is communicated through graphs. So the horizontal scale on the graph, which is the x-axis, so the bottom one, tells us the depth at which each measurement was taken. The depth is in meters. A meter is about the same distance as a yard. The important thing to see is that if you move right along the x-axis, the numbers get bigger. Thus, the farther to the right on the graph, the deeper the measurement was made. The vertical scale on the graph, the one that goes up and down, usually called the y-axis, tells us how much oxygen was in the ocean water. Notice that this measurement was done in percent. The numbers get bigger the higher they are on the y-axis. So the higher on the graph, the more oxygen there is in the water. Now look at the graph as a whole. Each dot on the graph represents a measurement. The first dot on the bottom left-hand corner of the graph. Looking at the x-axis, it is right on the O. This means it was taken at 0 meters in depth, right on the surface. Looking at the y-axis, it is also on 0, which means that there was 0% dissolved oxygen there. I said O earlier, and I should have said 0. My bad. Page 74. Just look at the graph. Just observe the graph while I speak. Now, look at the next dot. It's not very far to the right of 0, but it is pretty high on the graph. So what does this mean? If you look at the x-axis, you will see a little vertical bar with a 200 below it. This means that position of the position on the x-axis represents a depth of 200 meters. Now, the point we are looking at isn't far enough to the right of 0 to be to the 200-meter mark. Thus, the measurement was made at a depth somewhere between 0 and 200 meters. Since the point is far to the left of the 200-meter mark and only a little to the right of 0, then the depth must be closer to 0 than 200. The actual depth for the measurement of that point is 50 meters. So look at the y-axis. Based on the height of the point, we can say that it is very close to the 0.6 mark on the y-axis. So this particular point represents a measurement made at 50 meters and indicates a 0.6% amount of dissolved oxygen. Okay. Do you see how to read the graph? The horizontal position of each dot represents the depth at which the measurement was taken. The vertical position of each dot, up and down, represents the amount of dissolved oxygen at that point. When the dots are between two markings on either axis, you can guesstimate the values by noting which mark the dot is closest to. Now that you know how to read the graph, what does it tell us? Well, once you actually get below the surface at depths greater than 0, the amount of dissolved oxygen is pretty large. After all, the dots that are to the right of 0 are high on the graph. Since a high vertical position indicates a lot of dissolved oxygen, depths between 0 and 400 meters seem to have a lot of dissolved oxygen. The dot just to the right of the 50-meter measurement is the highest dot in the graph. This means that there is more dissolved oxygen at that depth than at any other measured depth. Since that dot is about halfway between the 0 and the 200 mark on the x-axis, that means it was made at a depth of 100 meters. Once the measurements go below a depth of 400 meters, the amount of dissolved oxygen starts to decrease. The dot that is halfway between 400 and 600 meters seems to have the lowest amount of dissolved oxygen. Since it's halfway between the two, what depth would that be at? What depth is the dot that is between the 400 and the 600 meters? What depth was that measurement taken at?
I'm just gonna say 100 because I don't need to say 100.
Baby. 400 to 600. What's in between 400 and 600, sweetie? Thank you. We got to turn on our brains. So, what level was the fourth dot taken at? No. Count your dots. Start at 0 down at the bottom of the graph. Go up to the next one. That's 2, up one more, 3, down 1, 4. What level was that? What depth of measurement was that dot taken at?
Not four.
Honey, go down. Find the 4th dot and then go down. What is it above?
I was counting the numbers.
No, the 4th dot.
The question was again.
What depth in meters was the 4th percentage, the 4th dot, taken at? Your depths in meters is on the bottom row. All those numbers down there.
500.
The 4th dot.
I was counting one dot.
Start at the 0 down at the bottom corner. Go up 1, up 1 more, then back down a little bit, and that's your 4th dot. Go down, baby. Down. Straight down from that 4th dot. 1, 2, 3, 4. Down. No. 4. Yes. Straight down. No, don't follow the dots down. Go straight down. There you go. Okay. At what level was the 7th dot taken? Baby, down. Down. 7 dot, not percent. Dot. Count the dots.
The 7th dot, correct?
Mm-hmm. The 4th dot was 200, baby. So the 5th dot would be 250. So what would the 6th dot be? if the fourth dot's 200 and the fifth dot's 250, what would the sixth dot be?
300.
Then what would the seventh dot be?
400.
Nope, you missed.
350.
There you go. There you go. Okay, we will keep working on graphs either tomorrow or Monday next week. You can try to do the module questions on the graph, but I'm not sure you're ready to do that just yet. So if you want to look at it and see, and then if you have trouble, it's okay. Graphs always trip people up. Honey's like, yes.